Hey guys, you're watching Python tutorial videos on my YouTube channel Python for Microscopists. In this video, let's learn a little bit about the bag of visual words. And this is used for image classification. And again, this example is going to be image classification and not pixel segmentation. So if you remember in the last few videos, we talked about random forest and generating features and segmenting every pixel in microscope images or any image in general. Yeah, so that's a semantic segmentation or pixel level segmentation. So now we are trying to classify it. You have a whole bunch of cat images, dog images, and you're trying to say, okay, these are cats and these are dogs. So it doesn't matter at a pixel level what's happening when it comes to this application. It's basically, okay, what is the image belong to? What class does the image belong to? So a classic example for this, for example, in microscopy would be, is this, let's say, is this a malarial infected cell or is this a healthy cell? Okay, or if you are a metallurgist or if you are a geologist, let's say, or even in mining, you look at a whole bunch of images and certain types of ores, even though the chemistry may be the same, they probably have different textures, right? It can be iron oxide, but one type of iron oxide, you have a certain type of texture because of the way it got formed, versus the other. So how do you classify different textures? Yeah, so and this can be a very good approach, actually, the bag of visual words. So let me start by talking about what do we even mean by visual words. Okay, so let's go to the drawing board. So now try to guess who this person is who may have said these things. Okay, so one of the things, let me start by, okay, because this is in the news, I'm sorry about the, okay, witch hunt. Okay, sad. What else? Fake news. Okay, if you're from the US, you probably know this right away. Fake news, and also look at the exclamatory mark. Okay, and a very sick person. Let me keep looking. Nasty lady. Okay, so if you guess this right, I'm pretty sure, I mean, most of you probably guessed this right. In fact, on the other screen, I'm just reading out some of the words from the Twitter feed of our president, Mr. Trump. Yeah. And again, obviously, I'm not trying to get political in this discussion here. Whether you like the guy or not, you can agree that, okay, these terms typically remind you of Trump, right? So how do we know that? Well, that's because we are trained to this type of terminology by being exposed to a whole bunch of tweets or talk coming out of Trump. So this is how we know that, okay, this is this person. So in our minds, we are actually segmenting this, or we are actually binning these words into certain categories, and we are like, okay, this behavior collectively. If I only said sad, you probably don't know. Maybe it is Trump, but it can be anyone, right? If you say witch hunt, probably it is. I mean, that's a good chances that you guess that this is Trump. Same with fake news. But certain keywords by themselves, like just a sick person, you don't know what the context is. Only like nasty lady, you probably don't know. But when you put all of these together, you're like, okay, now I know that the story fits Trump. Okay, so this is in a way, this is how the text analysis is actually performed, right? So when you're trying to analyze certain text, you can automate the process, and there are algorithms that are called bag of words, okay, where certain keywords are extracted from sentences, and a histogram of the keywords are actually prepared, and then you kind of compare it with a trained model and say, okay, there is a this much probability that this text belongs to whatever, this document or something. So along the same lines, let me delete this whole thing. Along the same lines, the bag of visual words, as the name suggests, this is based on this concept of bag of words. Now, in the bag of words, we just saw that we have a bunch of words, right? and we look at some keywords like, nasty or something, and we look at their frequency. Okay, so over the last few tweets or something, the frequency of these words is this much, and now we do a histogram plot. Okay, and then we compare with other documents or other tweets like I mentioned, and then we extract this. Think of exactly the same workflow, except instead of words, we are actually classifying images. Okay, so each word is a part of our image. So if you have an image with let me try to do a really cartoonish human face. Okay, so if you have like a human face in any of your images, there are like, okay, eyes, there is nose, depending on which direction. Let me draw the hair that I have, curly hair. So anyway, and I look like a devil, but that's okay. uh, so we know that this is human face. That's because there are certain key points, like, okay, ears, this has eyes, and it has nose, it has like a mouth, so this must be a human, right? There is a whatever probability that this is human. And the way we are doing that is again by looking at individual components and putting them together. Okay, so this is basically the bag of visual words. Now the question is, okay, I can see it, but how does the computer know that, okay, this is a nose or this is an eye? In fact, it doesn't need to. It doesn't need to know the individual components as long as it identifies the key points and then extracts them. Okay, just like the keywords, we are extracting the key points here. Okay, for a bicycle, it can be like a pedal, seat, tires, and so on. In fact, I just Google searched for an airplane. If you look at this, as humans, we can say that these are all airplanes. That's because it's got a big body there, it's got a tail, tail wing, it's got like these wings. I cannot see the wings here, so in my word, I mean, for this image, that's not a high probability that's going to give us or tell us that this is an airplane. But then there is this front wheel and two back wheels, right? So there is a front wheel, two back wheels. So the front wheel, two back wheels. So these can be the key points, front wheel and two of these ones. Okay, so these can be the words or key points if you want to call them. Okay, so that's going to help us identify. So we need to extract those key points somehow and describe them mathematically. Okay, just by telling in words is fine, but you need to extract them and describe them mathematically. And luckily, we have something that can do that. And again, if you watched my previous tutorials, I had one video on key points and descriptors. SIFT and ORB and a whole bunch of other ones. So please go ahead and watch that tutorial. So we can take that. Now, once we have the key points, once we know there is a nose or a whole bunch of noses, on different images, once we have the keywords and descriptors, we need to cluster them into various types, right? So we need to cluster, okay, these are all the eyes from hundreds of images. Okay, so you need to cluster them, and cluster of noses and cluster of ears. Now, uh, like I said, in reality, we don't care which feature is what. We don't care that this is a nose or ear, as long as we know that this cluster, belongs to one class and this cluster belongs to a different class. And again, if you watched my previous tutorials, you know how we can do that. You can use k-means algorithm to do automatic clustering of the data. Okay, so once you cluster these, then you need to look at the frequency of the vocabulary. Okay, so step one, like I said, key points. Okay, so key points, if I can write it, and then k-means clustering. Let's say once you have this k-means clustering, you can use any clustering, but k-means is usually the best way. So once you extract key points, the second step is k-means clustering. And once you get the k-means clustering, now you need to look at the frequency. How often are these showing up in an image? So you actually create like a histogram of this. Okay, I have these many noses, these many times I see the eyes, and these many times I see something else. Again, we don't care if it is an eye or a nose. It's just that, okay, feature number one, feature number three, or cluster number 1, 2, 3, and 4. This is the histogram. Okay. Uh, Now, once we have this frequency, from a programming side point of view, we need to vectorize this. Okay, so well, before doing that, again from a programming point of view, the next step, typically the next step is to normalize the histogram, because we don't want histograms of completely extremes, skewing anything. So we need to normalize this, and in fact these histograms are, this is our bag of visual words. I mean, this histogram right here, this is our bag of visual words, where we know, okay, what words and or what key points and what is the frequency. Okay. Now, mathematically, these histograms need to be represented as vectors. Okay. So a machine learning algorithm can be trained to discriminate these vectors. Okay, corresponding to positive and negative training images. So if I have like a positive images that has a whole bunch of pictures of ice, and a bunch of images with no ice at all. So I need like vectors corresponding to the positive, vectors corresponding to the negative, so I can use a machine learning classifier. And let's test both support vector machines and random forest, okay, for this bag of words. So once it's all done, we can save the model and apply it on future images. That's pretty much it. So I hope this is clear. Okay, so this is again, all I can do is, as part of this training series, tell you the fundamentals of programming, different algorithms, key points, k-means clustering. But this is the first time, I believe, like the bag of visual words is where we are thinking about, okay, what did we learn? So what do we have in our knowledge base? What kind of tools do we have? And how do I take these tools and put them together to form a application that does something for us? In this case, the application is image classification, and the toolkit that we are actually using is, of course, reading a bunch of images and then detecting the key points, and then k-means clustering and histogram and vectorization and support vector machines or random forest, and saving the model and applying it. So we learned all of these tools. So let me jump into the code. I know this is going to be a long video anyway, so to save a bunch of time, I have written the code and I'll go through a few lines so you can actually see the structure. And I really encourage you to write your own, but let me just go through the code and then let's look at the results. First, let's have a look at the files. So let me open my folder structure here. So I have two folders. First of all, I have like a dataset right there. I'm in a folder called Dataset. Within the Dataset folder, I have two folders. One is for testing, one is for training. Okay. Let's start with, again, I have another folder here that's called cell images. And within cell images, I have testing, and then I have training again. So we'll get to the cell images in a minute, but let's start with an easy example. Okay. So here I have three classes. Okay. I have under train, I have all the images I want to use for training. And the way I organized here, again, it's up to you how you want to do it. Okay, you can actually dump a whole bunch of images, but then appropriately label them as airplane, bicycle, or car. I chose to create three folders, and each folder contains corresponding images. Like airplane, I have like a few airplane images, not many, 17 airplane images that I'm going to use for training. And similarly, I have bicycle and car images. Now, under test, I have also some images. Under test, I think, again, for airplane, I have three images. And same thing for bicycle and car, three images each. So the plan is to train the algorithm using the images that I have in train, and validate them on the data set that I have in test. And then let's move on to the cell images. Okay, so now let's jump into the code. So as usual, I start by importing the standard libraries. So let me zoom in one more bit so it's easier for you to see. Just importing the OpenCV, NumPy, and OS. OS is again to handle my folders and file structures. And then I defined what my training path is, and started off with empty lists that I can fill later on for image paths and image classes. Okay, and again, at this point, I don't know what the image classes are, but since I stored my files in appropriately labeled folders, my image classes would be, okay, read the folder name and then make that a class. Okay, make that a class ID. That's exactly the plan right there. So down here, again, this is pretty standard, walking through the folders and defining the training path. which is my folder path right there, and the training name. And again, you can, it's self-explanatory right here. Again, we went through so many, of these videos. Again, it's a waste of time for us to go through every line right there. But eventually what it is we are creating a class ID. So I'm saying that, okay, my airplane, instead of calling it an airplane class, call it class 0, class 1, class 2. Okay, that's what the class ID is, because that's obviously the best way to handle our classes. Then we have to create the key points and detectors. Again, I explained that this is nothing but uh, again, if I can go back to the picture again, the key points are nothing but, okay, this is my nose, this is my eye, these are my ears, or whatever the interesting points are in airplanes and everything. And how do you select interesting points? By the way, you don't have to use a predefined key point detector or something. You can just draw like lines. Oh, sorry, I'm using my mouse, so it's a bit. So you can actually draw some. Let's say, take every 10th pixel. Take every 10th pixel. Okay, in the image. So you can actually apply a regular grid. This also works very well. I think this is called dense sampling. But anyway, you can say take every 10th pixel, and that is your key point, and extract a detector. But we can use pre-built detectors, and that's what I'm using here. Something called BRISK, B-R-I-S-K. In fact, in Python 2 and OpenCV2, my favorite detector was SIFT, SIFT. It's not available anymore in OpenCV. So I had to find the next best one, which turned out to be Brisk. And I also experimented with something called ORB, and that did not give me good results. So I'm like, okay, let me switch that and put Brisk here. Again, that's for this application. If you have a different type of application, maybe ORB does a better job. It's up to you to experiment with various key point detectors and descriptors. Again, I had a different talk about it, so I'm not going to again dwell too much time here. Now, we are walking through every image, and we are actually detecting and computing the key points, and we are storing them into into the list that we created up here. That's pretty much it. Okay, so we are, as you can see, we are extracting the key points, and we are extracting the descriptors, and we are actually saving the image path, yeah, which is the image name. Let's say, I think that's the image name that we are extracting. Okay, and associating with the image name the descriptor that we get from this step. Now, we need to stack all the descriptors vertically in a NumPy array, again, because we need to convert that into a vector, because we need to feed that into a support vector machine or random forest. So and also, of course, before doing that step, we need to do a k-means clustering on these descriptors, that we just created. Now, the k-means clustering, I didn't know this, but in scipy.cluster.vq, the k-means, again, you can bring k-means from somewhere else. But when I tried this, it said, okay, you cannot do k-means on this, because these are a bunch of integers. So I had to convert that into a float. That's the only reason why I converted that. Okay, and then we are performing k-means clustering. Again, I am using k-means from scipy.cluster.vq. VQ stands for vector quantization, and with 200 clusters. I actually tried with 100 clusters. The accuracy was low. We'll see that when I run this. We can look at the results. So k is nothing but how many clusters do we want to divide this into, and then we have our descriptors that we converted into floating points. So we should have a floating point descriptor right there. Okay, so once we have the k-means, again, the next step, as I described, once we have the k-means, the next step is to create the histogram of these features. So now that we created these clusters, let's count them and create a histogram. So that's what this part does down here. And then we do the vectorization here. Again, I'm pausing this, so if you want to copy the code, you can. Let me move this right-hand side so you can see the whole thing. At some point, I can share the code on GitHub or somewhere, but I really want you to put in the effort, because that's the only way you learn, by typing this. And of course, here I'm doing the quantization, vectorization, and then the next step is basically, again, as you can see, well, apparently I didn't describe it here, but the next step is machine learning. So I have code. Well, actually, I forgot about normalization. So the histograms again can be, we don't want them to be, skewed by these complete outliers. We want to normalize everything. So that's exactly what we have done here by removing the mean and scaling to unit variance. That's pretty much it. Okay, so that's what we have done here. And finally, the final step, using a support vector machine. Actually, using machine learning algorithms, like I mentioned in many of my previous videos, is literally 2 or 3 lines. Getting the data to the point where you can feed it to the machine learning algorithm, that's where bulk of the time goes into, right? So now we defined the linear, well, I defined linear SVC here with total iterations of 50,000. Again, I tried, like, if you don't give any value in here, the default is 100. And my accuracy wasn't good enough, so I tried 50,000. Okay, it worked great. You can try, again, it depends on the type of sample, type of images you're working with. And down here I commented of the random forest, but we can try this once we try this linear SVM. And finally, what did I do? Yeah, so we're done right there, but we want to use that to segment future images. So I actually use joblib. That's also available in scikit-learn to dump this to dump my objects, the Python object into one single file, and I called it BOVW, like bag of visual words dot pickle file. So I'm actually dumping everything in there. Obviously, this file is the training file. Okay, so this is where I'm actually training using a bunch of images that are in the training folder. Then for validation, I am going to, let me go ahead and zoom in. The code is exactly the same for validation for the most part. We are doing exactly the same key point extractors, and in fact, I copied and pasted the same code, except the only thing I kind of removed was the k-means clustering. We don't need to do that anymore. Obviously, once we have the vector, that can directly go into our, our algorithm right there. Okay, once it's done, I mean, once we are actually predicting, okay, the test features, once we are predicting, then the next step is just printing out what is the true class and what is the prediction class. Is my airplane being labeled as an airplane or not? So that's what I'm doing down here. And of course, I added another section to print out the confusion matrix. And if you're confused about what that is, you will see when we execute the code in a couple of minutes. Okay, so that's pretty much it. And I kind of commented out this section. This is basically nothing but, okay, if you have a whole bunch of images that you want to classify, go ahead and do that, and dump a CSV file. So you can open the CSV file and see, okay, my file number 1, what is the label? File number 2, what is the label? Or image number 1, image number 2, and so on. That's pretty much it. Okay. Uh, Again, I really do not want to make this an extremely long video. That's why I'm not typing as you're watching the video. But I hope you can at least pause the video and look at the code and try to understand and digest exactly what's happening at every step. Okay, now is the fun time. Let's go ahead and run this and see exactly how the output looks like. But before that, let me zoom on to the right-hand side so we can read the code, read the output a little bit clearer in the video. Again, the key things here before I run, the key things that we need to remember. So it's looking at the train folder in dataset, okay? And the train folder in dataset right there. And it's going to create the classes called airplane, bicycle, and car. And finally use how many clusters? Divide this data, the key point, extract key points, divide it into 200 clusters, and then does this, and then uses SVM. Okay, so these are the key components here. So let's go ahead and run the code. There you go. Even on my laptop, with only 4 cores, I'm not multi-threading this. Even on my laptop, it is literally, it's pretty fast. And by the way, I should actually, yeah, in this case, we only have a handful of images. We'll talk about how many images when we get to the cell dataset. So now we should have a file named bovw.pickle in our train folder. So if I go back to my bag of visual words, there is BOVW.pickle, and again, I'm recording this on October 17th, as you can see, and it just saved this file. So now let's go to validate and then run this. So what validate is doing is the first line, it's reading this file that we just saved, okay, BOVW.pickle file, and then it's unpacking the classifier that I called CLF, the class names, this is the scalar and the number of clusters and the vocabulary, okay, and then it's using the same down here in this code. So let's go ahead and run this, and now we should see what the accuracy is. This is great. I mean, this is an easy one. Let me expand this right hand side so you can see it a bit clear. And by the way, down here we are actually printing, we are printing the true class and the prediction, right? The true class, aeroplane, 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 and my prediction says aeroplane, aeroplane, aeroplane. That's great. Bicycle, bicycle, and everything. So down here you see the confusion matrix. So this is nothing but, okay, all my airplanes are labeled as airplanes. All my whatever the second one I think is bicycles, and all my cars. And this is a visual representation. So now let me change something, because I said if I change the number of clusters. Okay, let's go to the training part and change the number of clusters to, I don't know, let's change it to 100. Okay, and then run this one more time. Okay, so now it created a new pickle file, and now we can go ahead and run the validate again. So now let us see. So by changing this number of clusters to 100, now my accuracy has dropped from 100% to 88.9%. So looks like my first airplane image has been misclassified as a car. Okay, and now you can see the confusion matrix. So this is airplane, this is the car column. So on x-axis I have airplane, I'm sorry, think of this as having airplane as the first row, bicycle as the second, and car as the third row, and the first column airplane, second column bicycle, third column car. So we want to see everything along the diagonals, and everything other, it's not doing a great job. Okay, so this is, again, there are many parameters to play with. So that's why I'm not comfortable when people talk about random forest being more accurate than support vector machines or something. It completely depends on the data that you are feeding through this. So if I actually keep this at, let's say I change this to 1000 linear maximum number of iterations for SVC, and go ahead and run this. So it's okay. So now it's trained. Now let's see if it has any effect on the accuracy. Well, it doesn't seem to have any effect on the accuracy right now. Okay, so I could have actually left it to 1000. So this is our support vector machines, segmentation using support vector machines. And now we can do the same for random forest. Okay, uh, so just for the fun of it, let's the easiest way to do this is comment out the k-means and then uncomment the random forest. Obviously I need to uncomment this, and let's do exactly the same. Oh no, we don't have to do this in validate, because it's just creating the model in the train part, right? So let's go ahead and run this. So by the way, I'm using number of estimators as 100, okay, as part of random forest. Okay, that's trained now. So now let's go ahead and run the validate. Okay. Well, the accuracy is pretty much the same, about 89%, except it misclassified the car as airplane and not airplane as car. That's the only difference here. Again, you can change the number of estimators. You can change the k-means. Oh, by the way, I think we can truly compare support vector machines and random forest in this case. Although for random forest and support vector machines, the only parameters I'm changing here is maximum number of iterations and the number of estimators. By going to the k as, for example, 200, when we do k-means, I'm hoping to get my 100% accuracy there. Okay, training done. And again, we are using random forest right now, and let's do the validation. So, well, still it's not it's not as good as support vector machines under these settings, okay, under these conditions, which is 1000 trees, sorry, 100 estimators, and for support vector machines, our iterations were 1000, okay. If I actually do 100 iterations, it wasn't converging, like I said. So use whatever you think is the best. So now let's actually go ahead and this is fine. This is easy, right? I mean, uh, let me go back to the data and look at the data itself. One thing that's incredible is even with limited amount of data, like training data, so for training, airplane, we have 17 images. Bicycles training, we have 17 images. So each of this, we have 17 images for training, and we still got pretty good accurate values there. But again, these are simple scenarios. So for to make it a little bit more complicated, I actually obtained cell images from the Kaggle website. I go ahead and Google search for malaria data sets, for deep learning, then you'll probably find this. So this one is right out of there, but except the only thing I have done here is I took a subset of those images. I took about 240 of those images. I resized all of them into like 128 by 128, and I used them for training and testing. So I saved about 100 images for training, 104 images for training each for parasitized and uninfected. And I also saved for testing, I believe 130 some images. Yeah, 136 images for testing. And the testing images are completely different from the training images. So there is no overlap here. So the images that we are going to use for testing, the system has never seen them during the training process, which is incredible. So this is why I think this is a slightly more difficult challenge, even though in this example, we only have two classes. Okay, and by the way, the code in this case is written such a way that it's actually counting the class IDs up. So I don't have to tell the software that, oh, I have two classes, three classes, four classes, or five classes beforehand. It looks at number of subfolders within that folder, and then it assigns the classes, right? I mean, in this case, it is only two, parasitized and uninfected. In the previous case, it was three. So I can have any number. I can have, like, even I tested this on 17 different classes, and it actually did a pretty good job, provided I gave enough training images. So let's go ahead and test this. So first thing first, let me comment my training path here. I made this so it's easier during the video process. So now it's going to look at the folder called cell images and train. And let's do the same here. We need our test images coming from, where is it? Not from there, but from cell images / test. Okay, so let's start by running the training process. And again, the classifier, let's leave it to random forest, 100 estimators, and let's leave the K to 200. Okay, so we can compare everything apples to apples. That was very fast training. My image sizes are small. So now let's go ahead and validate them. There you go. So now it actually worked on all of my 136 images, and it printed out. In fact, I should have commented it out. So parasitized and all of that, and then it actually came up with this. So now let's look at the accuracy. That's horrible. Well, horrible in the sense it's not as good as we want it to be. It's 64.7% accuracy, and it got 78 right of the uninfected or sorry, of the parasitized or infected, and it got 98 images correct of the out of 136. Okay, so we have 136 images that are uninfected and 136 images that are parasitized or infected. So of those, it only got 78 correct here and 98 correct here, which means it got 58 wrong there, 38 wrong here. On total, it gives an accuracy of 64.7%. That is not good enough. So let's see. First of all, let's see if changing. Again, I haven't done this, so I hate to do this on live. video, but let's just divide this into 500 clusters. And does that actually help? Okay, now let's go ahead and validate this. No, it's not going to help. Now it actually went down. So it's not that, okay, having a lot of clusters always helps. It's just that sometimes it's limited, by what it can do. So let's go to 200 and maybe if you wonder, okay, how about 1000 trees estimators instead of 100? Let us try that. Okay, now let's validate. Same thing, 64.3%. Remember, we had 64.3% even before right there, 64.7. So it did not help. It definitely did not help going to 100. So it is what it is. That is the limit that we have using this approach. Okay. So how about doing the same except for support vector machines? So now let's actually use support vector machines and see if it is any better with 1000 iterations there. And let me comment this out. So let's train it. It's done training, and let's validate this. Okay, so support vector machines, the accuracy is even worse, 56.25, and random forest we got 64.3. And in fact, I consistently get much better results on random forest on most of the images that I try to analyze. And again, we can even try playing with this maximum number of iterations. How about 10,000 iterations? So an order of magnitude higher. And running this one more time, still 58.4% accuracy. So this is the limitation of traditional approach for this. Now I can actually include all the 19,000 images that are part of this data set that you can get from Kaggle, but still the accuracy is not going to be as good as what you would get from deep machine learning. This is exactly why the deep machine learning field is taking off for these type of classification issues, especially if you have a lot of data. In this example, for malaria dataset, I have a lot of data because someone did a great job classifying them, cropping all these malarial cells and classifying them, or labeling them, I should say. So in the next tutorial, let's actually look at what deep learning is and what are neural networks and how can we use that on this same problem and can we actually get better accuracy, using deep learning. And I try to make deep learning as easy as it can be. And for that, we use a library called Keras. And please stay tuned and watch my next video. You're going to love it because I hope, at least I'm trying to make machine learning as easy as possible. So even rudimentary programmers can do it, write some code and start doing these classifications with minimal effort. So see you in the next tutorial, and thank you very much. Please like this video and subscribe to my channel. Thanks.